Hello, this is Joe, and I'm going to continue my lecture on Apache Spark that I started before spring break. Sadly, I can't be here in person to give you the lecture, so I'll do my best with this online lesson. So, we'd already gotten through quite a bit talking about the primary abstraction of Spark, that being the RDD, and how it represents a logical table partitioned across a cluster of machines and managed by Spark. And we talked about the transformations you can use to modify the data on those machines, and we talked about the actions which ultimately force the evaluation of those transformations and then bring the data back to the driver program. All the examples we talked about were with flat data. With integers, with strings, and those were the examples. But in reality, most of the data that we deal with is more structured in some way. And the most common way that data are structured is in some sort of key value form. And there's many, many different examples of that, and we'll talk a little bit about those going forward and how Apache Spark manages this type of structured data. So what are some examples of key values? Well, of course, there are maps in Java, there's dictionaries in Python, there are SQL tables keyed by ID, there's any number of different key value stores that you might be familiar with. And Apache Spark is actually tuned to perform operations on this type of data in such a way that data that share the same key will you can perform an operation just local to those data. So it doesn't necessarily cross keys, and we'll see some examples of these types of operations, actually transformations, that you can perform by key. So whereas the RDD was the primary abstraction for performing transformations and actions in Spark, it continues to be so. However, when we start talking about key value pairs and managing that type of data, Apache Spark has the pair RDD abstraction. Now, a pair RDD, it sounds like a subtype of an RDD, and I think that logically that's actually a good way of thinking about it. So it is an RDD. All of the operations that you can perform on an RDD, you can also perform on a pair RDD. However, it allows additional operations as well. It's not an official subtype of an RDD, but because of the way it's structured, in other words, the fact that it is structured as keys and values, Scala recognizes this, and through its through its mechanisms allows you additional methods that you can apply to these, and those are the by key based aggregation operations that you can do. Okay, so in addition to those on the pair RDDs, it also allows join operations. You're familiar with those from your database work. We also saw those earlier this semester. There were a number of examples where you guys went over joins. And in terms of performance, it allows parallel operations by key. So, since all the operations are local to the key, they can be done in parallel. whether it be on different machines or different threads on the same machine. And another capability that pair RDDs allow is, since most of the operations are by key, the key becomes the natural partition mechanism. So you can tell Spark that you want to localize all the related data, the data that shares the same key, to the same machine. And then when you do some sort of an aggregation operation by key, or when you do a join, all the data that shares the same key will already be on the same machine, and thus reduce communication costs. So, how do we create a pair RDD? Well, as we said, it's a key value pair, which means it can take any key as long as it's serializable, and it can store any value as long as it's a value that Spark supports. And it can be arbitrarily complex, both of them. And the mechanism that it uses in Scala is a tuple. As long as your RDD is full of tuples of size 2, which are actually called pairs. So as long as your RDD is structured as tuple size 2, with the first element being something that's hashable, and the second element being some arbitrary type that you want to store, the payload, then it's implicitly going to be a pair RDD. And we'll see an example of creating a pair RDD in a second. The motivating use case that we're going to work with uses the same data that we talked about before and you're familiar with. It's the weather station data. In the prior examples, we were calculating average temperature across all stations. But now we're going to show you various ways to calculate average temperature by station. A much more useful operation, probably. So here's the structure of the data. You probably remember this from some of the original homework you did. This is the station ID. This is the date and time. This is the type of measurement, in this case a maximum temperature. This is the temperature that was read of this type. And then there's other fields that we're going to ignore. So here's an example of creating a pair with these data. Well, again, we need a key and we need a value. Naturally, if we're going to perform operations by station ID, then that becomes the key. So that's the first field here. And the data that we're going to use is the temperature. And so that's the fourth field here. So creating a pair, or in other words, creating a tuple of size 2, is as simple as declaring an immutable variable, a label. In this case, it's called station temp. And these parentheses here indicate that we're defining a tuple. The first element of this tuple is the first element of the fields array. Now you probably remember how we parse the fields array. We'll see this in another example. But we take the first element of the fields array, that's the station ID. So that's the first element of the tuple. And then for the value, we take the fourth element of this string array here, which is the temperature, and we parse it as an integer, and that becomes the value. So the key is station ID, value is the temperature. That's exactly what we're looking for. All right, so let's look at the full code to create this pair RDD with station ID to temperature key to value. This is very familiar code to you. We'll talk about it up above, but the first thing is that we use the Spark context to read all the input files in the input folder, and distributed out to a cluster of size 3. So that creates this RDD right here. Actually, well, this is the intermediate forms. So ultimately, station temperature is going to be the end result, but we have a chain of operations. This is the first, this map is the second, and then this is the third. And so we're going to sort of show how this chain of operations consecutively accomplishes creating the station temp pair RDD. So this is the first transformation, and it just simply loads the file. And so now we have all the strings, which are each line of the file, distributed across 3 partitions. Now the second transformation we do is a simple map, and for each line of the file we tokenize it by comma, because commas are the delimiters between the fields of the data. So that creates this second intermediate RDD, which is of type array of strings, which are the tokenized fields of each line. Okay, and then this third map is which is basically what does the work in creating the RDD. For each, it takes a function, of course, and so for each array of strings that comes in, because remember we've got an array of strings coming in, it creates a pair. In other words, it creates a tuple of size 2. And this is exactly the code that we saw right here to create a tuple of size 2. It's just doing it for every single array of strings in the RDD. In other words, for every single record that we originally have. So now we have the end result, which is station to temperature, that's the name of it, is this pair RDD keyed by station ID and then carrying the temperature as its value. So now we have a pair RDD. What can we do with it? Well, quite a bit actually. Here are some of the common pair RDD operations or transformations. They're transformations because they don't actually execute. They're lazy, and then they execute, of course, when an action is performed. So what can we do? Well, we can reduce by key. And then this is pretty straightforward. You remember reduce from before. It takes a sequence of values and converts it into a single value by taking an appropriately formed function. So it reduces a sequence of values with the same key into a single value. And that's what this signature is showing you here. Here's the function that takes 2 values. One of them is the accumulator going along. The second one, of course, just like this is talking about reduce again, this is the element that you get each time you iterate across the sequence, and it reduces it down to a single one. So this will collapse it down to ultimately to a single value of type A. Fold by key is exactly the same thing as reduce, except you get any arbitrary starting value that you want. You don't have to use the first element of the sequence as the starting value. So we'll see this when we want to do a count, for instance. We don't want to use the actual temperature as the starting value. We want to use 0 as the starting value. So there's a use case for wanting fold by key, and we'll see that in an example. Now, combine by key is even more powerful. And it takes a function to create the starting value. It takes another function to combine the values by key on each partition. And then it takes a function to merge these values by key across partitions when they're collected back together. So this is a much more involved function, but generally sort of the same function, the same type of functionality as reduce and fold by key. Okay, map values. This doesn't collapse things down to a single value the way the prior three transformations did, but this simply takes a function and applies this function to each value of a key. So it can just change the type of value. It doesn't change the key, but it changes the values associated with that key, and ultimately you get the same number of values for every single key because it's a map function, and that's the semantics of a map. Similarly, flat map values is exactly the same type of thing, except that the function that is mapped across all the values must return a sequence. And thus you might end up with, and then the sequence is flattened out the same way map values work, the same way flat map work with a single RDD, or flat map works in general. And that is then the sequence of values are then appended together at the top level. So ultimately you'll get a a full pair RDD of this type here, as opposed to a pair RDD of sequences, which is not what you want. If that wasn't completely clear, just review the difference between map and flat map. Same thing here. Okay? Okay, other transformations here, you can get just the keys if you need to work with them. You can get just the values absent of their keys if you want to work with those. You can sort by key. That makes sense. For every given key, you can just sort the elements within them. This is kind of expensive. And then there's group by key. Group by key just basically brings all the values for a given key together. And it's kind of an expensive operation unless you're actually going to do something with them like these. So the transformations up above implicitly call group by key themselves. So this isn't probably something that you're necessarily going to have to do, but but it's there regardless. So those are the operations. Then there's set operations as well, because remember, now that we have these key values, it's in a very useful form that we would. So just as we would with any sort of tabular data, you'd want to join it. You would want to, perform the intersections. You'd want to perform the union, the subtractions, and those functions are all available to pair RDDs. And it uses the key as the join attribute, if you will. So you folks know what a join is. This is an inner join. It takes only the keys that are common to both RDDs. It takes two pair RDDs, and it joins them together. And then similarly, you have the left outer join and the right outer join, where it carries the semantics of those that you're probably familiar with from database. I'm not going to go into the specifics of those. The subtract by key will remove the elements with one key that are present in another RDD. So you just want to keep, in this case, it's not the intersection, you're removing everything within the intersection and keeping everything else. And co-group is sort of like in this group by key, in that it's not something that you might not necessarily use this directly, but the join operations use it internally, because it sort of first does the join by key and then returns you an iterable sequence of the values for the two different RDDs. In this case, types V and W, and you can do any arbitrary thing that you want with these RDD, so you can build your own semantics that are outside of doing a join or a subtraction. If this isn't completely clear, look up cogroup and some of the things that you can do with it. But again, it gives you a little more flexibility, but it's not something that you necessarily will use all the time. I just put it in here for completeness. Now there's actions, of course, and you know what actions do. They force the evaluation of the transformation and return a result back to the driver. So you can count the elements by key, and then there's a collect action as well. And I sort of warn you not to do a collect when we're working with RDDs because usually there's so much data. But if you properly reduce it down by key, and it's not that much data, this collect as map actually might be something that you would want to consider. If you just want to look up the values for a specific key, you can do that as well. Now there's one I left out of here, and that is to save as text file. And that essentially works the same way as the action within an RDD. It takes the pair RDD, in this case all the tuples, and it collects them down and writes them to whatever destination storage you have on HDFS or locally or wherever. And we'll see an example of that call. But that is an action as well, save as text file. Okay, so this example is going to is similar to what we had before. It's calculating the average temperature, but instead of doing it across all stations, it's doing it by individual station ID. So it's pretty obvious what we have to do here. First, we have to parse the data by station ID, and then we need to perform the average calculations by key. So that's exactly what we're going to do. This is logic that you saw up above to create the pair RDD. Okay, let's go through it quickly. We parse the file. We tokenize the strings for each line, which are the temperature readings. We filter out only the ones we're interested in. We want to keep the maximum temperatures and throw everything else out. And then finally, we create the pair RDD by taking this array of strings and keeping only the ones we want. The first one, the station ID, is the key. The temperature integer is the value. And we're going to persist it because, as you'll see later on, we use it twice. And we don't want to perform this whole expensive calculation twice. So, the first thing we have to do is, well, in any average calculation, you need the sum and the count. And we're going to do these separately. So to create the sum by key, we're just, again, like we did with the full data set, we're going to perform a reduce, but we're going to do it again by key, so we're not crossing the data values by key, and we pass it the reduce function. The reduce function takes two integers in this case, the accumulator that goes along, and each individual element that we iterate through, and it collapses it down to a single one by adding them together. So that's pretty straightforward. It's going to sum the temperature, the total temperature, by station ID, and that's what we want. Now we also need the count to be able to do the average. So we're going to do a very similar thing, except in this case we can't use a reduce, because reduce uses the first element of the sequence, in this case the RDD key values, the values, as the first element. And we don't want that in this, but instead we want to start the count at 0. So we need to use a fold, because the fold allows us that functionality. And so we start with a 0, and then we pass it the function that we're going to apply to every single element of the list. Here's the aggregator, the count that comes in, and then here's the element, the temperature element itself, the value. And notice that we don't even use the value, of course, we just need to increment the count, because we're only counting, has nothing to do with the sum. Now, we have two pair RDDs here, right? We have sum by key and we have count by key. These, unlike when in the original example where we did it globally, those were both actions. Reduce itself was an action and fold itself was an action. So those values came back to the driver program, and we did the average calculation locally to the driver program. But here, these are still RDDs. It still actually could be quite a bit of data distributed distributed amongst the Spark cluster. So in this case, we need the sum to come together with the count, so that we can calculate the average by key. So in this case, we're going to appropriately use a join. So what we're going to do is we're going to take the sum by key, and you know what that is, we just calculated it above, and we're going to take the count by key and we're going to join them. It's naturally going to join on the station ID. So in this case, we're going to have the station ID is still going to be the key, but we're going to have the result is going to end up being placed in a tuple. The first element of the tuple is going to be the sum, and the second element of the tuple is going to be the count. So that becomes the value of sum count by key. And when we see average, you'll see how this value tuple is used. Okay, so now we want to calculate average by key. So we take this new pair RDD that we have, we just created in the line above, and we're going to map a function across it. And this function is going to take each element of the RDD, and it's going to produce what? Well, it's going to produce another tuple. Okay, so obviously the result's going to be another pair RDD. The first element of the tuple is the first element of sum by count, which is the station ID. So we're going to maintain the keys. But the second element of the tuple is the first value of the result, which is the sum. Okay, this is Scala. You need to be familiar with Scala. This is how you get the first element of a tuple. Okay, and we're going to take the sum and we're going to divide it by the second element of the value tuple, and that's the count. So we do sum divided by count, and that gives you the average. We return it as we return each value keyed by its station ID, and we have average by key, which is a pair RDD. And then we're going to perform the action, which ultimately is going to do all the work, save it as a text file in the output directory. So this average by key RDD will be written to the text file, and I would encourage you to execute this. You'll see what it looks like. It's just going to have the key, and then each tuple is going to be written out as the key, comma, the value, in this case, the average. So that's how we use pair RDDs to calculate average. Note we did have to use station temp twice, and that caused some inefficiencies that we're going to address now with data partitioning. So when we created these station temp here, we created all of these tuples keyed by station ID. But what we never said was where these tuples reside in terms of what machines. They could just as all the keys of each type could just be randomly or arbitrarily distributed on any node of the Spark cluster. So that when we start to perform these operations, we need to do a lot of shuffling to bring these keys together. And so what we can do is Spark gives us operations to sort of, since we're sort of aware of the algorithm that we're trying to do, we can give Spark hints on how to properly partition our data. And in this case, the most useful one for us is to control the set of keys such that they reside on the same node. So if you think about it, all these by key operations, if you can guarantee that all the keys reside on the same node, then all the computation is local to that node. In other words, it doesn't involve shuffling data across and between nodes in advance of performing the computation, and thus minimize the network traffic between the nodes to improve performance. Now there's a couple different ways to partition. There's the hash partitioner, where you give it a number of buckets, which pretty much should be the same as the number of nodes you have in the Spark cluster, and it will use its hashing function on the key to distribute the data so that you can be guaranteed that each key resides on its own node. Similarly to what we saw in MapReduce with total order partitioner, there's also a range partitioner, and in that case it's a little more involved because you have to give it the range of values that you want on each node of the Spark cluster, and it'll take care of partitioning those values, those keys, to the different nodes that belong inside of that range. This is a little more involved. If it's something you're interested in with sorting, then you might want to look up range partitioner. We're going to use hash partitioner because in our case, we just need to know, we don't care exactly which keys are on which nodes. We just care that all the data for a given key, for any given key, is on the same node. And again, it's only useful for key-oriented operations. The ones we saw with just normal RDDs, it doesn't matter where the data are. It's going to ultimately have to communicate across the nodes anyways. Now, once you partition the data by key, these operations will maintain that partitioning. In other words, they won't mess it up so that you have to hash partition again. So all joins will maintain the partitioning. All by key transformations will maintain the partitioning. This makes sense. This sort of the values again makes sense. It will not corrupt the partitioning by key. And then if we only work with the values, in other words, we don't do any sort of operation against the key, operations such as map values and flat map values and filter, of course, only operate on the value or remove a value in the case of filter, so there's no shuffling that happens between the machines, so thus the partitioning is going to be maintained. And this is important. And you'll see that we use code below, and we would like this guarantee that our partitioning is going to be maintained. So how can we modify the above code, which I said is, does this twice, so that we can remove the inefficiencies of having to shuffle for both of these transformations. And we do that with the partition by function. So remember where we were. This is the pair RDD station temp. Okay, so this was the RDD full of tuples, station ID to temperature. Now, if we declare, or if we apply the partition by method to it and give it, in this case, tell it we want to use a hash partitioner to hash to 3 buckets, in other words, each corresponding to our 3 nodes, this will perform the shuffle for us. It will move all of the keys so they're co-located on their, with all their other similar keys on the same machines, and then we can use the persist function so that it's materialized and it doesn't need to be done a second time. So then any future operation we do that uses these joins or by keys transformations will maintain the partitioning. So let's look at this these two lines of the code we had above. So I'm going to move back a couple slides. Do you remember these two here? Well, if you think about it, the pair RDD we created above, the keys could be on arbitrary machines in the cluster. So when we do the reduce by key and then we do the fold by key, in both of those cases we have to shuffle the data by key to perform them. So we're performing a shuffle twice, and this is inefficient, and this is what we're trying to get away from. So if we instead do this partition by first, then we only need to shuffle once. So that's what we're showing here. So if this is the exact same code, we're doing the reduce to get the sum, and we're doing the fold by key to get the count. But in this case, it's using the previously partitioned RDD that we created right here. It's already been shuffled, so all the keys are co-located, and it's much more efficient. It doesn't need to perform a shuffle for each one of these two. Whereas if we didn't use this previously partitioned pair RDD, we would have to perform a shuffle each time, and that's what happened in the code up above. If you start talking about a large amount of data, you can see that that would be a really expensive operation to have to perform the exact same shuffle twice, and that's what hash partitioning helps you avoid. All right, combine by key. This is sort of the last big example that I'm going to show you. Now remember that when we calculated the average by station, we actually had these two operations. One to reduce by the key to calculate the sum, and then one to do the count. But why can't we do that in one operation? And the answer is we can. We can do that with combine by key. Now this is a really powerful pair RDD transformation. And I'm not going to walk you through these first four lines. They're exactly the same as we saw before. It does the tokenizing and the parsing, creates the pair RDD, and that's called temp by key. Notice we're not doing a persist, and we're not doing a hash partition, and that'll become clear in a moment because we're not doing the multiple operations. We're only doing one single transformation, and that's combine by key. Combine by key takes three functions. The first function creates the starting value. Okay, in this case, it takes the first value, and in our case, we want to create a tuple with the value itself and a 1. So this is the starting value. You can probably see what's forming up. The first element of this tuple is going to be the sum, and the second element is going to be the count. And yes, this should be a 1 because this is the first element, not a 0, as we did with the fold. Now it takes two other functions, and this is similar to the combine that we saw with RDDs. This function here is used per node, per partition, and it has to have, and because of its semantics, it has to be different than this second function, which we do use when we merge across partitions. And this is exactly the same thing we saw in the first lecture. So when we accumulate the sums and the counts on an individual partition, we take the accumulator, which is the input, okay? So it's a tuple, and the first element of the tuple is the sum, second element of the tuple is the count, the running count, and we take the value, the current value of temperature value. And what we need to do is collapse that down and return another tuple. It has to be the exact same type as this accumulator input. And this resulting tuple is going to take the first field of the accumulator tuple, which is the sum, and we add the current value. It takes the second field of the accumulator tuple and increments it by 1, and that's the running sum. So as you can see, this is going to calculate the individual, the per partition sum and count, and have it sitting as a tuple. But then we need to combine these tuples across the partitions. And as I said, this is a little different. This takes this combined takes all the individual tuples, which are going to be in this form that came from these combiners, and it's going to, in this case, add the sums. Makes sense, but it also has to add the counts, because one doesn't make sense anymore. You're not just accumulating a single count. There would be multiple counts accumulated into this sum. So then the end result is going to be, once you finish the merge, it's going to be the sum of all the temperatures on the different nodes, as well as the sum of all the counts on the individual nodes. And then from there, you can do your average calculation by key, because it's combining it by key, of course. All right, so here's a picture of that. Here we are with temperature by key. This is the pair RDD with the key and the temperatures. Here is the here's the function here to perform the per partition accumulation. So it's simply adding up the sums and adding up the counts, and it stays local to the partitions. Okay, it doesn't matter. It doesn't need to perform any sort of shuffle in this case, because it just reduces it by key. But then when we perform it across, then when we merge it across all of the partitions, then because the semantics require that the result comes as a key value pair, with the key being the station ID and the value being this result tuple that comes from this merge function. At that point, we need to co-locate all of the keys, the keys that share the same key value to the same machine, and then we can perform the merge. I think that makes sense. But the point is that this combiner here runs regardless of what the key is, and it collects it by key. And then at the time we need to perform the merge, in other words, the second function here, at that time it performs a shuffle. So in this case, we don't need to do any persisting, and we didn't need to do any hash partitioning, because we didn't use things twice. Okay, it naturally had to do a shuffle, but we didn't need to say save the value of the shuffle or do that shuffle right now, because it was this was a much more linear operation than we did up above when we used the separate reduce by key and fold by key and then join, which is more of a tree structure in calculating, because we calculated the sum with the same data, and then we calculated the count with the same data. We joined it back together. Two different ways to accomplish the same thing. Now, the last thing I'm going to cover is doing joins within a loop. Now, this is something that you're going to need to certainly do for the PageRank program. So this sort of contrived example says, okay, say you've got an array of RDDs with individually by year. Okay, so for what you want to do is you want to calculate some time series based on the very first year. So we're going to create a static RDD for this very first year, and then we're going to loop through the other 9 RDDs, and we're going to join them together and do some time series calculation, which we're not going to specify here. But the point is that once we join once we join this first year with the latter years, then we're going to perform some time series function. So now, why do we need to do what this example is illustrating is that it's important to, because we're reusing static RDD multiple times inside of this loop, it's really important that we partition it by key, and then we persist it. So these are these 2 mechanisms that we've learned. Persist, so it is materialized, it doesn't need to recalculate it again, and hash partitioning, so that it's already been shuffled, so all the keys are on the same partition, and it doesn't then need to be done separately every time that it's involved in a join. So that's illustrated here. Static RDD is been previously created. It's been previously partitioned and persisted. So then as we loop through the latter 9 years and join the static RDD with each individual year's RDD, only the individual year RDDs need to be shuffled before joining. The static RDD does not. It's already been done so. If this hash partition weren't here, then we'd have to shuffle the static RDD every single time, and it could be very, very expensive. This is a tip. Don't forget to use this in your PageRank code, because I think you'll find a very, very similar pattern when you get to it. Okay, so if you haven't already, these are some of the best resources I found for installing Spark. And these are some of the general resources to learn about Spark. The Spark in Action is actually my favorite. It's a very new book by Manning. This is an older one, and it's really a lot's been superseded by the latest version of Spark, and this is well covered in the Manning book. And Manning also talks a lot about the Spark internals. So it might be really interesting to you folks who develop a keen interest in Spark, and I hope you do. It's a really, really exciting technology, like I said, and I'm glad you had the opportunity to use it in this course, and I'm really glad I had the opportunity to tell you what I know about it. So thanks for your time. I know it was a lot, but I think it was all worthwhile, and ultimately I think it could become very, very useful to you. So thanks a lot for that. And thanks to the references I used to put all this together. So have a good one, folks.